This is the part 2 of 2 videos on exponential and logarithmic functions. The part 1 has discussed the basic things about exponential functions, and now in this part 2 we're going to discuss the logarithmic functions. Let's start our discussion with this equation. 4 squared equals 16. This equation can also be expressed in a logarithmic function as 2. So the exponent or the power here is now starts the sentence. 2 is the logarithm of 16. 16 is from here. 2 is the logarithm of 16 to the base of 4. So the base here, 4, becomes the base as well in the logarithmic function. And this 2 is the logarithm of 16 to the base of 4 can also be written formally in a logarithmic function as 2 is the logarithm of 16 to the base of 4. Or if this equation is expressed in an exponential function, the 16 here can be replaced by y, and the 4 here is the base b, and the 2 here is the independent variable. The y is the dependent variable, and the t here is the independent variable. So when this y equals b to the power of t is expressed in an exponential function, it becomes t. So the t here is coming from the exponent. It is coming from the power here. T is the logarithm of y. Y is from here. The logarithm of y to the base of b. So the b in the exponential function also serves as the b in the logarithmic function. So we can say that basically the relationship between t and y is the same as the relationship between t and y in the exponential function. So we have the same relationship between y and t, both in the exponential and in the logarithmic function. Only it is expressed in a different way. In exponential function, the dependent variable is the y, and in the logarithmic function, the dependent variable is the t. Let's pay attention again to this exponential function. Y equals b to the power of t. We know from the logarithmic function, the t here is equal to the logarithm of y to the base of b. So when the t here is replaced by this logarithm of y to the base of b, we can find this equation. b to the power of the logarithm of y to the base of b is equal to y. So now we know that this exponential function can be expressed in the logarithm function this way, and also it is basically the same as this equation. Now let's see another example. Now we're gonna find the exponential equation from logarithmic equation. Here we can see 3 is the logarithm of 1000 to the base of 10. This logarithmic equation can be expressed in an exponential equation as here the base here is 10. It is 10, the base in the logarithmic equation, and the 3 here becomes the exponent equals the 1000 here. The same way we can find the exponential equation from this logarithmic equation. 10 is the base, negative 2 becomes the exponent, and then the 0.01 is now placed here. And If the base in the logarithmic equation is 10, we can write it as log here without any information about the base. If we do not find the base here, usually we assume that the base is 10, or sometimes it is also written with the base here, the logarithm of something to the base of 10, and it is usually called common logarithm when the base is 10. And when the base is e, the natural number, usually we write it as the ln, or natural logarithm. Or in a more complete way, we can write it as the logarithm of something to the base of e. It is natural logarithm. Let's discuss natural logarithm more. When we have the natural logarithm of e to the power of 3, it is equal to the logarithm of e to the power of 3 to the base of e, because in natural logarithm the base is e. So it is the same as the logarithm of e to the power of 3 to the base of e, and it is equal to 3. To show that it is correct, let's see the exponential version of this equation. The 3 here is the exponent, the e here is the base, and the e to the power of 3 is moved here. So we can see here that e to the power of 3 is equal to e to the power of 3. It means that if we have the natural logarithm of e to the power of 3, it is equal to 3. So the 3 here is coming from the 3 here. It is always the same number. So when the 3 here is replaced by 1, it is equal to 1. When the 0 is placed here, so it is equal to 0. When the number here is -1, it is equal to -1. And when we have e to the power of 0, it is equal to 1 here. So the natural logarithm of 1 is 0. And then the natural logarithm of 1 over e is the same as e to the power of -1. It is equal to -1. And there are some rules in logarithm. The first one, the product rule. The product rule says if we have the logarithm of u times v to the base of p is equal to the logarithm of u to the base of p, so here u to the base of p plus the logarithm of v to the base of p. And then in the quotient rule, the logarithm of u divided by v to the base of p is equal to the logarithm of u to the base of b minus the logarithm of v to the base of p. So when it is a product rule, so we have a product here of u and v, the sign here is plus. When it is a quotient, the sign here is minus. And in the power rule, the logarithm of u to the power of a to the base of p is equal to a times the logarithm of u to the base of b. So the a here is moved to the front here. And log base conversion. The logarithm of u to the base of p can also be written as the logarithm of e to the base of p times the logarithm of u to the base of e. See here that the number here, e, should be the same as the number here. So when it is in natural number, the base here should be also in natural number. When the number here is, for example, 5, the base here should also be 5. And the p here is moved here. So the base here is the same as the base here, and the u here is now placed here. And then if we have logarithm of x to the base of p, it can also be written as the logarithm of x to the base of e divided by the logarithm of b to the base of e. So the base is now moved here and the x is now moved here, and the number here should be the same as the number here. So the base here should be the same as the base here. If the base here is a natural number, this one should also be natural number. If the base here is, for example, 10, the base here should also be 10. And inverse of a log base. If we have the logarithm of e to the base of p, it is equal to, so the logarithm of e to the base p is the same as 1 divided by the logarithm of p. Now p is not the base anymore, it is now here, and the e now becomes the base. The logarithm of e to the base of b is equal to 1 over the logarithm of b to the base of e. Let's see the graphs. From previous slide, we have seen that the relationship between the dependent and the independent variable, or y and t in this example, in exponential equation is basically the same as the relationship between t and y, or the relationship between the dependent and independent variables in logarithmic function. So the relationship between y and t here is basically the same as the relationship between t and y in logarithmic function. The only thing different is only the dependent and independent variables. When y here is the dependent variable, now in the logarithmic function it is the independent variable. When the t here in the exponential function is the dependent variable, now in logarithmic function it is the dependent variable. So because y is a function of t, so in the vertical axis we can find y, and t is on the horizontal axis. And in the logarithmic function, now the vertical axis is for the t and the horizontal axis is for the y. That is why we can see here that the relationship between y and t is basically expressed in this graph. This relationship between y and t is basically the same here as here. For example, when the t is 0, y is 1. The same thing here. When the t is 0, y is 1. The graph here looks different just because now the t is placed at the vertical axis, while initially in exponential function the t is on the horizontal axis. So the graph here, the logarithmic graph here, is like the mirror image of the exponential graph. When the t equals y or y equals t is the mirror. So this is the mirror image of this one, or this exponential graph is the mirror image of the logarithmic graph. Let's see the derivatives of exponential and logarithmic function rules. Let's start with the exponential function rule. When we have y equals b to the power of a function of t here, this is a function of t. So the derivative of y with respect to t is the first derivative of the function here, the derivative of the function, times the b to the power of the function here, times the natural logarithm of the base b. For example, when we have y equals b to the power of 3x squared plus 2x, the derivative of y with respect to x is the derivative of the function here, so it is 6x plus 2 times the b to the power of 3x squared plus 2x here times the natural logarithm of the base b. Another example, when we have y equals b to the power of t, the derivative of y with respect to t is, the derivative of t is 1, here 1 times b to the power of t times the natural logarithm of b. And then the logarithm function rule. When we have y equals the logarithm of a function of t to the base of b, the derivative of y with respect to t is the derivative of the function here divided by the function times the natural logarithm of the base. For example, when we have y equals the logarithm of 3x squared plus 2x, this is the function, to the base of b, the derivative of y with respect to x is the derivative of 3x squared plus 2x, which is 6x plus 2, divided by, here, 3x squared plus 2x times the natural logarithm of the base. And another example, when y equals the logarithm of t to the base of b, the derivative of y with respect to t is the derivative of the function, the derivative of t is 1, divided by the t here, t, times the natural logarithm of b, the base. Now, the rules of the derivatives for base e. First, the logarithmic function. When we have y equals the natural logarithm of a function of t, the derivative of y with respect to t is the derivative of this function divided by the function. For example, y equals the natural logarithm of 4 plus 2x cubed. The derivative of y with respect to x is the derivative of this function here. So it is 6x squared divided by 4 plus 2x cubed. Y equals the natural logarithm of t. The derivative of y with respect to t is, the derivative of t is 1 divided by t. And then the exponential function. When we have y equals e to the power of a function, the derivative of y with respect to t is the derivative of the function here times e to the power of the function. So, for example, when we have y equals e to the power of 4 plus 2x cubed, the derivative of y with respect to x is the derivative of the function here, which is 6x squared, times e to the power of 4 plus 2x cubed. And then y equals e to the power of t. The derivative of y with respect to t is, the derivative of t is 1 times e to the power of t, e to the power of t. So, the derivative of y with respect to t of this exponential function is the exponential function itself. Let's see the slope of exponential function. This is a typical shape of an exponential graph. Y equals b to the power of t. Y equals b to the power of t. And this is the derivative. The derivative of y with respect to t is the b to the power of t times the natural logarithm of the base, That's what we can learn from our previous slides. And then the derivative of this derivative, or the second derivative, so the derivative of this with respect to t is, using the same rule, the b to the power of t times the natural logarithm of b here times the natural logarithm of b. So it is equal to b to the power of t times the natural logarithm of b squared. As long as b here, the base, is greater than 1, the b to the power of t will always be positive. And because b is greater than 1, the natural logarithm of b will also be positive. So we can conclude that because b to the power of t is positive here, and the natural logarithm of b is also positive, so the first derivative must be positive as well as the second derivative, because we can see here b to the power of t and the natural logarithm of b squared. So both the first and the second derivative must be positive. When the first derivative is positive, it shows that the slope is positive. When the slope is positive, it shows that the original function, or the y here, must be increasing. We can see here y always increases. And then when the second derivative is also positive, it shows that the original function is the first derivative. The first derivative of the slope must also be increasing. So when the second derivative is positive, we can conclude that the slope of this exponential function increases, or exponential function increases at an increasing rate. So we can see here the slope is always positive, positive slope, but we can see here that the slope increases. It is getting steeper. When we move from left to the right, it is getting steeper. When it is getting steeper, it shows that the slope increases. That is why here the first derivative is positive. It shows that y increases, and the second derivative is also positive. It shows that the first derivative of the slope of this exponential graph increases. So we can conclude that an exponential function here, this is an exponential function, this is the exponential graph, increases at an increasing rate. And then the slope of logarithmic function. This is the logarithmic function, y equals the natural logarithm of t, and this is the shape of the graph. Y equals the natural logarithm of t. The first derivative of this y equals the natural logarithm of t is 1 over t. And then the second derivative, so the derivative of this derivative, using the simple power rule for derivative, it is negative t to the power of negative 2, or we can also write it as negative 1 divided by t squared. As long as the t here is positive, anyway, we cannot find the natural logarithm of negative number, so t is always positive. The 1 over t will always be positive as well. So the slope of this logarithmic function will always be positive. See here, the slope is always positive. The slope is always positive. Y always increases. And then the second derivative here is negative 1 over t squared. Because t is positive, so negative 1 over t squared must be negative. So the second derivative is negative. It shows that the original function, the original is the first derivative, must be decreasing. See here, the slope here, the slope of this logarithmic function, of this logarithmic graph is decreasing. It is getting flatter. When we move from left to right, the slope is getting smaller. The shape of the graph here is getting flatter. So that is why we can find here that the second derivative is negative. It shows that the slope decreases. So the conclusion here, logarithmic function increases at a decreasing rate. The slope here decreases. It is getting flatter. Let's do this simple exercise to apply some of the rules we have learned from previous slides. We have y equals x squared divided by x plus 3 times 2x plus 1. The natural logarithm of y is the natural logarithm of x squared minus, we have a quotient here, so we need to apply the quotient rule. Because it is a quotient, so the natural logarithm is the natural logarithm of x squared minus the natural logarithm of the things here, the natural logarithm of x plus 3 times 2x plus 1. And then we have a product here, so we need to apply the product rule. The natural logarithm of x plus 3 times 2x plus 1 is equal to the natural logarithm of x plus 3 plus the natural logarithm of 2x plus 1. And then we can open the brackets and we can find that the natural logarithm of y equals the natural logarithm of x squared minus the natural logarithm of x plus 3 minus the natural logarithm of 2x plus 1. And then let's find the derivative of the left side. The left side is natural logarithm of y. So the derivative of this natural logarithm with respect to x is the derivative of y divided by y. And then the derivative of y here can also be expressed as the derivative of y with respect to x. So the left side, the derivative of the left side is 1 over y times the derivative of y with respect to x. And then let's find the derivative of the right side. This is the right side. The derivative of this right side is equal to, we have natural logarithm of x squared. The derivative is the derivative of the function here, as this is the rule as the one we have applied to this one. The natural logarithm of y is the derivative of y with respect to x divided by y. So when it is applied here, the first derivative of this function with respect to x is 2x divided by x squared. And then for this one, the derivative is the derivative of x plus 3, which is 1, divided by x plus 3. And then the same thing is applied here, 2x plus 1. So the derivative is 2 divided by 2x plus 1. And then when this equation is simplified, we can find the derivative of the right side is 2x plus 6 divided by x times x plus 3 times 2x plus 1. And the rest of the explanation of this exercise will be discussed in the next slide. From the previous slide, we have found that the derivative of the left side is 1 over y times the derivative of y with respect to x. And the derivative of the right side, from the previous slide, we have found that it is 7x plus 6 divided by x times x plus 3 times 2x plus 1. And then the y here can be moved to the right. So we have 7x plus 6 divided by x times x plus 3 times 2x plus 1 times y. And then the y here can be replaced by the information that we have from the previous slide. From the previous slide, we know that y is x squared divided by x plus 3 times 2x plus 1. And then when this whole expression is simplified, finally we can find the result. The derivative of y with respect to x is x times 7x plus 6 divided by x plus 3 squared times 2x plus 1 squared. I think that's all. Thank you. I hope this video can help you get the basic understanding about exponential and logarithmic functions and their derivatives. I hope we can see again in the next video. Thank you.